this optimization problem using local information only. And what is local information? That means that each of the nodes can only compute some of the function values or some of the gradient values, and the information coming from the nodes next to them. So let's say the simplest problem that you can imagine is the consensus problem or average consensus problem that is described as follows. So imagine you have a network of m agents on a graph, and each agent holds an initial value x0i. And let's assume it's a real variable. And the idea is that we want to compute the average of all those initial values in a distributed manner. So how can you solve this optimization problem? And you can imagine that this is, for example, sensors of temperature, so temperature sensors, and you want to compute somehow the average temperature in a building. So you can, in this case, let's say this sensor is measuring 2, and this sensor is measuring 5, and then you want to devise an algorithm that is able to compute this average using local information only. And it is not hard to see that the average of those initial values are equivalent to the solution of this optimization problem, which is you want to find an x such that the average distance to the points xi are minimized. So how can you solve this problem? And this comes to the fundamental result in distributed optimization, which is the consensus algorithm. And what is the consensus algorithm? Is the following. So at each of the points I, in iteration k plus 1, we're going to construct next iteration as a weighted average of the information coming from the neighbors. Remember that matrix A could be representation of the graph, in the sense that Aij is 0 if information from node j is not coming to agent I. So this operation can be done locally because you only require access to the information that is provided by your neighbors. So this can be done in a distributed manner. And of course, this is a very easy result once you understand this, which is on the assumption that the graph G is connected, undirected, and static. So undirected, that means that the matrix A is symmetric. Static means that matrix A is not changing with time, and connected means that you can have any path from node I to node J for any pair Ij. And moreover, if you assume the matrix A is doubly stochastic, that means some of the columns and some of the rows are equal to 1. And matrix A is equivalent to the graph structure, which is a positive value if and only if the pair Ji belongs to the set of edges. Then the iterations generated by this algorithm have the following property, which is for all of the nodes in the network, in the limit, you're going to reach the average value of the values held by the network. Right? So this is the fundamental result. This is nothing new. This is known for many things. From linear algebra, you can easily prove. This is kind of trivial. So now we move, for example, now a little bit more complicated problem. Let's say a linear regression problem, a regularized linear regression. So you want to minimize a problem of this form when you have a linear regression here. So you want to find a parameter z that minimizes the distance between the output b and a linear prediction hc. And you also want to have some regularization of, so c is not too big. And the idea in the distributed case is that the information that you have, so the matrix B and the matrix H, are not stored in single location. So it's stored in a distributed manner in the sense that vector B is split into several parts, and one of the agents in the network only knows some part of this vector, so a segment of this vector. And the same, this matrix H is also stored in distributed manner, which is H only knows a single part of this vector. So ideally, you would like to solve the full optimization problem, but each agent only knows one pair HI and BI. one way to rewrite this optimization problem is that I'm going to explain this later, what I mean by this, which is now we have a summation of these functions, which is only local information. And this is related to the formulation that I showed you at the beginning, which is the problem that we want to solve. It can be written as summation of fi's. And this, you can consider this as one of these fi's. So the main analytical tool that we're going to use is going to be the graph Laplacian. So the graph Laplacian is one property of the graph that you're given, which is the following. So imagine, for example, here is a graph, a cycle graph of 5 nodes. And I'm going to define the graph Laplacian as a matrix, which is the size of the number of nodes in your graph, where the diagonal values of each of the points is equal to the number of neighbors that each of the nodes has. So in this case, it's 2 because, let's say, node 1 has 2 neighbors, node 5 and 2. Node 2 also has 2 neighbors, and so on. And then it's going to be a -1 if that node is connected to the other one. So, for example, here, node 1 is connected to node 2 and node 5. Right? Node 2 is connected to node 1 and node 3, and so on. So this is the graph Laplacian. And one, let's say, important characteristic of the graph Laplacian is the following, which is the null space of the graph Laplacian. It's equivalent to consensus subspace. What does that mean? That so if you have a vector here, x, such that all the entries in this vector are the same, then w times this vector is equal to 0. This is an important property for the graph Laplacian. And this also holds, let's say, for square root of w. This is the characteristic that we're going to exploit. And why this is important? Because now we can reformulate our original problem by constructing the following vector, xx, which is a very long vector whose size is m times the original size of the problem. So remember, m is the number of nodes in the graph. So now we have a very long vector, which is a stocks of the copy of the variable x of agent 1, agent 2, up to agent n. And then we're going to call the function capital F, the summation of the original functions. But now, this is important here, we're going to have not all the x's, but only one of the x. So this is the x held by agent I. So this is the important case here. All these values are the different ones, the local copies of the variable. But then once we impose consensus constraints, we can immediately see, like, if you solve this problem, which is a convex optimization problem with linear constraints, you can solve the original problem because you're finding a function that is in the consensus subspace that minimizes the sum of functions. So what we have done here is just rewriting the problem in a form that you can express easily as a convex optimization problem with linear constraints. And then we will see later why this is useful for our applications. So in this talk, I'm going to show a couple of results, which is for 4 cases that we have explored. And we are going to propose optimal algorithms in the sense that we show that the number of oracle calls that you require for each of these function classes is optimal up to logarithmic terms. And the 4 function classes that I'm going to present is, of course, strongly convex and smooth functions, only strongly convex and Lipschitz on a bounded set, only convex and smooth, or convex and M. Lipschitz also on a bounded set. These are the 4 classes of functions that I'm going to explore. I'm going to focus only on the first one for time, but then we can, if it is time, we can talk a little bit more about that one. So this is a table of state of the art in this area. So what you can see here is centralized approach. Of course, this is known since many years ago by the work of Nemirovsky and Nesterov. We know that if the function is strongly convex and smooth, what we have here is number of oracle calls that you require to reach epsilon solution, and this table is up to logarithmic terms, so that's why I'm not showing here the log 1 over epsilon, but this is square root of condition number, right? And we also have the same result for mu strongly convex for mirror descent or smooth or M Lipschitz. So this is a centralized case. And for distributed case, this picture was not complete. And this is many works with Lina, Alex Olszewski, John Ducci, Olszewski as well, Farias, Ian Nekoara, and Jokotevich. And what we have here is a very sparse table for different classes of functions that was not known, and also optimality is not achieved. So for example, here we have L over mu 5 over 7, which should be 1 over 2, right? So it's not optimal. And then recently, so there is a couple of results, including ours, where we have reached a point where we can say something about optimality of this method. So for example, for the class of functions that are mu strongly convex and smooth, the optimal convergence rate is m square root L over mu, which is just linear scaling with the number of nodes in the graph of the centralized solution, which is square root L over mu. So this is some of the fundamental results here in distributed optimization, which is the optimal convergence rate in the worst case is linear scaling in the number of nodes of the centralized convergence rate. So your algorithm should have this convergence rate. So m is the number of nodes in the network. So basically, if you have a network of m nodes, the number of iterations that you require is m times the centralized solution. And we showed that for the 4 classes that we explore, we achieve these optimal convergence rates. Yeah. So now let's go to the analysis tools. This is our original problem that we have. So we have a function with linear constraints. And later we will see what happens with the matrix A square root of W, and F is just summation of Fi's. And we're going to call this an approximate solution if your function f of x is epsilon distance to optimal value, and if the constraint violation is epsilon tilde. Of course, this is traditional literature on convex optimization. So the first thing we do is we construct the Lagrangian of this problem. So we move the constraints to the objective function with some Lagrangian variable y. And then equivalently, we can write this optimization problem now in the dual variable, the Lagrangian variable, where the function is defined as this maximization problem. And the interesting thing here is that by Demyanov theorem, we know that the gradient of this dual function is just a times x star, with x star is the solution of the local or sub-optimization problem at certain value of the dual variable y. So this is very important because we will see later that evaluation of the gradient, so oracle calls in the dual space is just a times x, where a, for example, will have the structure of your graph. So oracle calls in the dual space will correspond to communication rounds in your network. So this is this important primal dual relationship between the problems, which is in the primal space, oracle calls corresponds to let's say gradient evaluations and so on and so forth. And in the dual space, oracle calls correspond to communication rounds. So when you talk about optimality in the dual space, is the minimum number of communication rounds that your algorithm requires to reach some solution. Of course, at every iteration, then you will need to solve this optimization problem that requires oracle calls in the primal space. One important property here is the following, which is if your function f is strongly convex in the primal space, then the dual problem is smooth. So this is something that we're going to exploit. Of course, this is smooth with this parameter. And then if your function is smooth, then the dual problem is strongly convex on a subspace, also with this parameter. And okay, well, I'm going to ignore this. Of course, the dual might not be unique solution, so because you don't guarantee strong convexity there. But then your solutions are in the kernel space of the matrix A. More important, this is what I was saying. So the dual function is strongly convex only. So if your primal function is smooth, then the dual function will be strongly convex only on the kernel space of the matrix A. So this is, of course, now we have dual formulation of the dual problem. So immediately, okay, let's apply the fast method to the dual problem. So the way it works is, of course, you first compute solution of the local optimization problem here. And then this is gradient, right? Remember that this is gradient of the dual function. So this is local computation and then just the momentum term. And then we can immediately see that convergence rate of the dual problem is linear rate with the condition number of the dual problem. And we know these parameters from the conditions that I explained before, right? So what I've done now is I've changed the variables that I talked about at the beginning. So let's change A by W, and then a new variable Z by square root W y, and Z tilde by square root W of y tilde. And what we have here is that this xi, which is the local solution of the problem, only depends on local information fi. So this can be computed locally by each of the nodes. And then second step only requires also local information, because this is the information coming from neighbors only, right? Remember that this W has the structure of the graph. And then this is just a momentum term, but it only depends on I. So all these three steps can be done locally with local information. So when you apply fast method to the dual problem, then everything can be done locally. So these are the 4 cases that we explore. Of course, I'm going to talk only about the first one. So when the function is f strongly convex and L smooth. And the theorem that we have is the following. So assume that each of the functions are mu strongly convex and smooth. Of course, then the capital F function is also strongly convex and smooth, with the strong convexity the minimum among all of local functions, and smoothness the maximum about all the smoothness parameter of the functions. Then the theorem says as following. So assume that the capital function f holds this assumption. Then the output of the algorithm that I just described is an epsilon epsilon r solution of the distributed optimization problem if n, which is the number of iterations in your algorithm, satisfies the following. So it's bigger than square root L over mu and then psi of W, when we have here is the condition number of graph Laplacian, right? Lambda max over positive non-negative, non-zero eigenvalue of the graph Laplacian. So what we have seen here is that now basically we have same convergence rate as the centralized problem, but now we have to pay a price, which is square root of condition number of graph Laplacian. And this is related to number of nodes in the network, or the topology of the graph. So all the other cases, let's say when the function is not strongly convex, what you can do is, of course, use Nesterov regularization. So you add, we exploit the following result, which is you have a function phi. You add a strongly convex term here with mu sub hat mu. And then if you set hat mu hat small enough, then finding an optimal solution to the regularized problem gives you also approximate solution of the non-regularized problem. So if your function is not strongly convex, you apply Nesterov smoothing, and then you obtain also the result. And then if your function is non-smooth, you move to the dual and apply Nesterov smoothing, and there you go. And if you don't have either strong convexity on smooth or smoothness, then you apply smoothing on both terms, the primal and the dual, and you obtain the same result. So this is just I'm going to skip all of this, which is all the 4 theorems that I show you. This is the important table here, which is for the 4 classes of functions that we explore. We obtain the number of iterations that you require, number of communication rounds, which is exactly the centralized bound times square root of condition number of graph Laplacian. This is the main result. And more importantly is that we'll have the result that in the worst case for fixed undirected graphs, condition number of graph Laplacian is of the order m squared. So that means that in our case, we have square root of that. So worst case will be m dependency on the graph topology. And you can imagine this in the simple case. So for example, imagine a line graph. So it's a graph that looks like the following. Oops. Of course, for this graph, information from this node cannot travel to the last node in less than the number of nodes in the line, right? So this is the worst case. You need at least m steps to reach from the first to the beginning, so the worst case is that. And of course, usually we don't know r or rx, which is the initial residual between the initial variable and the optimal variable, but then you can apply, let's say, restarting techniques to estimate this value or adaptive methods, but I haven't not explored this yet. So now the question is the following. So imagine now that we want to solve same optimization problem, but we don't have real variables, but we are in the space of probability distributions. So we have the same network, but now in each of the nodes, we don't hold a number, but we hold a probability distribution. And the problem that we want to solve is a similar problem, but now we have to define a new distance d between probability distributions. So, and of course, when you have this problem, first thing that comes to your mind is a Wasserstein distance. So let's see how the problem looks like for the Wasserstein distance, and this is just historical context for the Wasserstein distance, which was originally studied by Monge and of course Kantorovich. So if you don't know, so Monge was an engineer for Napoleon. He was in charge of building forts for Napoleon. So the problem that they have every time they finish building the fort is that all the residual material came to some piles of dirt, and then there were holes all over the ground as well. So the problem is, okay, I need to find a better way to fill those holes with the residual material. So if you have some material here, or how can you move materials from one point to the other in optimal way? So he proposed this formulation of optimal transport. And the general definition of Wasserstein p distance between two probability distributions mu and nu is as follows. So is the lowest cost on the space of joint distributions with marginals mu and nu of the average cost of all the points in the space, right? This is the general case. I'm going to explore later the discrete case of this definition. And I'm going to explore particular for the case of images. So you can consider an image as a probability distribution over a finite grid. And what this picture shows is very interesting, which is, okay, now in the same way that originally we wanted to compute average of numbers, so now we want to compute average of probability distributions. So what is the best way to do it? So what's the average of images? The naive case, let's say the obvious thing that you might do is, for example, compute average of each of the pixels. So average of pixel 1, pixel 2, pixel 3, and then, but then let's say here we have a number of images with two circles, right, different locations. If you do pixel by pixel averages, what you might obtain is figure A, which means nothing. Right? It does not represent the original images. But then if you do Wasserstein averages, what you might obtain is this figure E, which is exactly 2 concentric circles. So what this shows is that this Wasserstein averaging preserves the geometric structure of your images. That means that my time is almost done, so I'm going to try to finish soon. So what this image shows is that Wasserstein distances are very useful for preserving the geometric structure of your data. Right? In this case, we have a bunch of samples of 2 concentric circles, and the average, the Wasserstein body center of all these images is precisely 2 concentric circles. So it's a good way to preserve information. And for the discrete case, the Wasserstein distance, the regularized, entropy-regularized Wasserstein distance between 2 finite distributions P and Q is the minimal cost of this optimization problem, which is the inner product between the matrix M and X. And we are optimizing over the space UPQ, which is the set of matrices with marginals P and Q. E is, of course, entropy. M is a matrix of cost between I and J. This is the Euclidean case, but you can have any other form here. And of course, this inner product, this is entropy, and this is the space of matrices with marginals P and Q. So the problem that we want to solve here is that given a set of probability distributions Qi, you can imagine this as being the images. So you're given a bunch of images Qi. You want to find a new image P that minimizes the Wasserstein distance among all of them. So somehow the body center is this definition, which is an image that in the space spanned by the Wasserstein metric locates in the middle among all these points that you have. And there are some results that people proposed by this, which looks like a consensus algorithm. Remember, exactly the same. It's just the averages of the algorithms that you have. But this is not very scalable because you have square dependency on the number of nodes and cubic dependency on the number of points in your distribution. So what we did is, of course, we used the formulation that I showed at the beginning, which is the linear constraint, consensus constraints. And we apply the primal dual function that I showed you. This is just a specific example. And then we can have corollaries of this form, which is for the barycenter problem. We have exactly iteration complexity, optimal iteration complexity with respect to the function problem and graph Laplacian. And we have other cases. So imagine now, let's look some simulation. You have a bunch of images corresponding to the number 7. And you want to compute the average of all these images with the Wasserstein metric. So if you do the Euclidean thing, you could just get a blob. That means nothing. But if you do the Wasserstein metric, then you have a 7 that preserves geometric structure. And then you want to solve this problem on a distributed case, which is each of these nodes in the graph only holds one of these images. That's the main problem. So let's see how does this look like. I'm going to move directly to the simulations. Can you click? Maybe click? No, okay, then open a file in the folder, yeah. Oh, here. And second option. Oop. No, then go to folder. Yeah, maybe this one. So what I'm going to show here is, yeah, pause. Can you go to the beginning? So what we're going to show here is for all the numbers, each of these rows hold a different image of the number 0, of the number 1, 2 through 9. And what we will see is that as the number of iteration goes by, which is time in this case, you will see consensus on the on the Wasserstein mean of these images, which is, let's say, a geometric representation of each of these images. So can you play it again? So you can see like all the agents agree on what is the Wasserstein barycenter of each of these images. Okay. Can you go to the slides?
Excuse me.
Yeah.
Question.
Yeah.
What's happening in the beginning of the process? Why do they all turn into some circles?
Yeah, this is just effect of the Wasserstein distance. So this is in the middle iterations there you lost the structure, but then they converge again to the barycenter. Yeah.
Okay, so it's not the effect of the method you use.
No, it's the effect of the metric that we're using. Yeah. 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 I can show later all the videos, but in order to finish on time, then go to the PDF again. Go next. Next. Yeah, there. So again, yeah. Just to go back to the original picture, so the type of problems that we want to solve is minimization of sum of functions over a network, where the network only knows one of these functions. And what we have shown is that we can build algorithms that can run over, can solve these type of problems with this specific information structure that we have imposed. And I will talk later at the end of the session that I have another talk about some challenges in distributed optimization, which the main challenge for me is the directed graphs. As of now, I have assumed all the graphs are undirected. That means that communication is bidirectional. There is a big open problem with directed graphs, which is the following. So imagine this graph here, which looks not too bad. So you have a line of nodes, but each of the nodes in the line, so this is directed only one direction, but then each of the nodes in the graph communicates back to the first one. Right here, this to the first one. Let's say. And now, let's say we want to compute the average, like consensus algorithm on this graph. And in particular, the best algorithm that we have for directed graph has this following property, which is x-axis is number of nodes in the graph. So let's say how many nodes do we have here? And y-axis is number of iterations that you require to reach epsilon solution of the consensus problem. And this is in the logarithmic scale. So even for a very small graph, let's say 40 or 50 nodes, you already need 10 to the power of 8 iterations. Which means that, and this is in logarithmic scale, which is for directed graphs, the best algorithm that we have depends exponentially in the number of nodes in your graph. And then it's a big open problem if you can design an algorithm that functions polynomially in the number of nodes on the graph for directed graphs. That's a big open problem. If you can solve it, then you become instantly famous. And yeah, that's I'm going to finish with this, and then if you have questions, we can discuss.
You considered only a deterministic algorithm?
In this talk, I have presented deterministic algorithms. We have a paper with Edward, which considers a stochastic case. And then Sasha and Darina Edward have an extended version for a stochastic case as well. Yeah. But the results are similar. You get exactly the same convergence rate as centralized case with additional price, the square root of condition number of the graph Laplacian. Yeah.
As for centralized.
Yes, yes. Yeah. Okay.